Back in 1825, Michael Faraday isolated benzene from the oily residue left by illuminating gas in London street lamps. Further investigation showed that the molecular formula of this compound was C6H6, a hydrocarbon comprised of 6 carbon atoms and 6 hydrogen atoms. In 1866, Auguste Kekule used his recently published structural theory of matter to propose a structure for benzene. Specifically, he proposed a ring comprised of alternating double and single bonds. And you see that shown right here. Now, in fact, Kekule had this famous dream where he was trying to come up with the structure of benzene. And like I said, they knew the formula was C6H6. And there were all kinds of interesting things proposed, or interesting structures. Like, for example, and I don't have a lot of space here, but there was something like this where they had 2 double bonds like this and then connecting these 2 carbons like this, or even kind of taking a triangle, right, something like this, and then making something like this. Okay, these are both C6H6, but they knew that this wasn't the correct structure, and I'm not going to provide much more background on it than that. But you can see that the arrows that I have shown here are equilibrium arrows, and that is in fact not correct, okay? Because Kekule suggested that the exchange of the double and single bonds was an equilibrium process, but we know that that is not true. And over time, his view was refined by the advent of resonance theory and molecular orbital concepts of delocalizations. And so the 2 drawings that we see here are now viewed as resonance structures, not as an equilibrium process. Now recall that resonance does not describe the motion of electrons, but rather resonance is the way that chemists deal with the inadequacy of bond-line structures. Specifically, each drawing alone, so meaning this one and this one, each one by itself is not adequate to describe the structure of benzene. The problem is that each carbon-carbon bond is neither a single bond nor is it a double bond, nor is it vibrating back and forth between these 2 states. Instead, each carbon-carbon bond has a bond order of 1.5, exactly midway between a single bond, which has a bond order of 1, and a double bond, which has a bond order of 2. And so to avoid drawing resonance structures, sometimes we draw benzene like this, okay, with a ring of electrons inside the aromatic ring. Now, you might see these if you're perusing the internet. However, I won't use them when I'm lecturing, and I recommend that you avoid using these because they're no good when you're trying to draw mechanisms which require scrupulous bookkeeping of electrons. And so throughout the remainder of this class, we're always going to draw benzene as it is shown here. Okay, so we're always going to draw it as alternating double and single bonds.